Hi everyone, and welcome to the lesson on using summation notation and approximating area under a curve. So as the title of the section suggests, we are going to begin with understanding the properties of the sigma notation. Some of you may have seen that previously in your pre-calculus classes. And then we're going to use the sigma notation to tackle a very important question in mathematics, and that is, how do we find area under a curve? We're going to begin by an approximation technique, and slowly we're going to work our way towards finding the exact area. So let's get started with our learning outcome number 1, which is understanding properties of sigma notation and learning how to simplify summations involving this notation. And again, please note that all of this will be important prerequisites towards understanding the rest of the lesson here today. So let's get started with properties of the sigma notation. First of all, what does even mean to put summation I from 1 to n of a sub I? What does that mean? So again, I'm assuming you have seen this in another class before, but just a quick refresher. You start with the lower index of 1. You keep incrementing it by 1 until you reach the upper index. And in the between expressions, you always put a plus sign. So a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. So it's a compact way to represent a sum. So for example, if we have summation I from 1 to 10 of just I, you would begin with I equals 1, substitute 1 in the place of I, that would be just 1, and then substitute a 2 and 3 all the way to 10. And if you add up all the numbers between 1 and 10, you would basically get what this compact sigma notation is indicating. And that will turn out to be, let's see, I'll do a quick calculation on the side and I'll show you later how that's done. Okay, this should be 55. I'll show you later how I'm getting that. At the moment, you can just put on the calculator. Okay, another example is summation I from 1 to 5 of I squared. Okay, in this situation, for every time you start with I equals 1, incremented by 1, you're going to plug it into the I squared quantity. So it's going to be 1 squared plus 2 squared all the way to 5 squared. And of course, we can do this, by hand. We can do it on the calculator, or there's even a summation notation in your calculator. I'm going to talk about that in a little bit. I believe it's under the math command, and you go all the way down. You're going to see there's a summation notation in there. And typically, I use the letter X because that's the easiest variable to enter in the calculator. So you can also enter the sum into the calculator with that command to find the sum. And if you enter this particular one, I believe this one also turns out to be 55. Let me double check on that. So I placed it into the calculator, and indeed it's turning out to be 55. And let me also quickly show you how to use the summation command, because what if this was like up to 25 squared? We don't want to one by one enter all those values. And as we're going towards our major goal today, which is understanding how to find area under a curve, we're going to do summations up to like 100 or 500. So the shortcut key definitely will be useful. So go to math, scroll all the way down, or you can go up. And I see my summation notation is right there. Now I have the fancier version of the calculator, and I'm going to use X equals 1, 2. In this case, we went up to 5, but remember that index could be any number, and it's going to be more convenient when you're dealing with larger numbers, obviously. And whatever variable you use here, use the same variable here. This was our squaring function, so X squared. And get out of the parenthesis, press enter. So there we go. Simple way of getting that summation of 55. Okay, what about sum I from 1 to 5 of just the number 4? If it's just a constant, when I is 1, you're going to have a 4. When I is 2, you're going to have a 4. So basically, it's always going to be the same constant as I goes from 1 to 5. So basically, you're going to have 5 4s. In other words, 5 times... Did I have too many there? Nope, 5. Okay, so 5 times 4, which will be 20. So let's remember that this is going to be one of our rules, that if you're just adding a constant, it doesn't depend on your index I at all. You can multiply that number with the upper number as long as I starts at 1. All right, so what about something like 2I plus 1 as I goes from 1 to 3? So start with the lower index at 1. That's 2 times 1 plus 1. Then plus start increment by 1. So I is 2. So that's going to be 2 times 2, which is 4. So it's going to be 4 plus 1. And increment it again. I is 3. So 3 times 2 is 6. So in each case, again, we're plugging the index into the quantity where you see an I, and then between the indices, you're always putting a plus sign because that's what sigma notation is telling us to do. So here we have 3 plus 5 plus 7, and that will be 15. Now let's do the reverse for a moment. Suppose you do have something given to you as a summation notation. How would you write that in the compact sigma notation? So in this case, you have 5 over 1 square, 5 over 2 square, and plus signs in between them, plus 5 over 3 square, plus 5 over 4 square. First of all, the top number 5 doesn't change, so I can just put as a 5. That one doesn't change. On the bottom, you're going from 1 square to 2 square to 3 square to 4 square. That is your variable, and the pattern there is I squared, right? I squared, where I goes from 1 to where? Where I goes, you keep incrementing by 1, the upper limit is 4. So this is how you would represent that summation with the compact sigma. Summation as I goes from 1 to 4 of 5 over I squared. And there are some properties of the sigma notation that it would be good for you to be familiar with. Again, some of you may already have seen these in your pre-calc classes. So for example, as I goes from 1 to n of just a constant, we've seen this already today, right? You would just multiply n times c. Now, what if you have summation I from 1 to n of a sub I plus b sub I? Okay, in that situation, you can distribute your summation notation over a plus or minus. So it'll be summation of the first quantity plus or minus summation of the second quantity, keeping the indices the same as I goes from 1 to n in both cases. And what if you have a constant times a sub I? You're summing this quantity from I goes from 1 to n. How do you simplify that? In that situation, you could actually factor out the constant c. Think of this as, let's say, c times 1 over n plus c times 2 over n plus c times 3 over n. So you could indeed take the c out and you will still have a summation of everything else. So you could write this as c times 1 over n plus 2 over n plus 3 over n, which this is the quantity you could write as a sigma notation. So just the constant c can be factored out from a summation, and because it doesn't have a pattern, it doesn't depend on I, so it can be taken outside of the summation notation, and the pattern then will still remain in your sigma notation. Okay, so that's a property of sigma that we should know. We can take out a constant multiple. We could take out c because c does not depend on I, therefore it's considered a constant. All right, a few more properties, and then we're going to do some examples with the sigma notation. And you don't have to memorize these summation formulas. I would provide them to you if they are needed on a problem. So first of all, summation as I goes from 1 to n of just I. So there's an interesting formula for this, which is n times n plus 1 over 2. This is what I was using earlier when I had to sum up all the numbers from 1 to 10. So n was 10, n plus 1 would be 11, and divided by 2, and I simplified 2 goes into 10 5 times. That's how I got 55 earlier today, because I knew this formula existed. And where does this formula come from? Sometimes you can prove these things with induction, but there's a really nifty way of proving this. So if you just even think about numbers 1 through 100, okay? If you just think about 1, 2, 3, all the way to 100, and I think it was Gauss who came up with this technique. And now go backwards. Start with 100 and keep subtracting. Say 99, 98, all the way down to 1. Now add up each of these. Like this is 100 plus 1 is 101. 2 plus 99 is 101. 3 plus 98 is 101. All the way at the end. 100 plus 1 is 101. Now how many 101s do we have? Because the numbers went from 1 to 100, there's 100 101s. But this includes adding them twice, going in ascending order and then in descending order, but you've added that sequence of numbers twice. So to compensate for that, we divide by 2. So think about it. If you were adding the numbers from 1 to 100, the formula would say 100 times 101 over 2, and that's exactly what we got here. So that's pretty cool, right? So yeah, there's a reason sometimes why these formulas work. It's nice when we can see them directly, but when we cannot see them directly, there is a method called induction, and we can actually prove that the formula is really correct. And again, you may have seen the technique of induction in your pre-calculus classes. So another formula is for the summation of I squared as I goes from 1 to n, and the formula is n times n plus 1 times 2n plus 1 over 6. Again, you don't have to memorize it, just know where to get it in case you need to refer to it. And then there's a formula for summation of I to the third power, which is almost the same exact as the first one, except you quantity square n times n plus 1 over 2. Now let's do some mixed examples using summation notation. So for example, if we want to add up all the numbers from 1 through 60, you could write like 1 plus 2 plus all the way to 60 and put in your calculator, but that's way too much work, right? If we can apply the technique we just learned, which is n times n plus 1 over 2, your n is 60, n plus 1 is 61, all over 2. And you could simplify this. 2 goes into 60 30 times. And then you can multiply 30 times 61 to get 1830. Now, I would invite you to pause the video right now, use the formula from the previous slide to do this one, summation of I squared as I goes from 1 to 20. So that's like 1 square, 2 square, all the way to 20 square, right? And in each of these cases, yes, you can also check on the calculator, but sometimes when we do area, we're going to need to see some patterns, and it's going to be important, especially when you have n and not just a number. It will be important to be able to recognize the formulas and use them. So for this one, the formula was n times n plus 1 times 2n plus 1. So that's 2 times 20 plus 1, 41, all over 6, right? That was the formula for summation of I squared. And if you put this into your calculator, you're going to get 2,870. And if I want to check that on the calculator, again, I can also use the summation notation. Just instead of I typically use X to make things easy to enter. And the older calculators, if you don't have the fancy summation notation, it might put something like this on your screen, sum of a sequence, but you can still enter. Let's say you're adding X squared. Sometimes it wants to know what's the variable. You put comma X, and it wants to know from where to where, let's say from 1 to 20. So this is how you can enter it using the older operating systems. Okay, summation of I to the third. So once again, we can go back and refer to the formula that we have just learned in the previous slide. Remember, that was the square of the first formula, so n times n plus 1 over 2 quantity squared. So your n is 15, so 15 times 16 all over 2 quantity squared. And again, you can simplify. 2 goes into 16 8 times. You do 8 times 15 and then square the entire quantity. You're going to get 14,400. All right, just a couple more examples using the sigma notation. And those of you taking Calc 2 are going to deal with the sigma notation quite a bit. There's an entire chapter there about, properties of sigma, applications, infinite series, and all kinds of applications and so forth. So it'll be good to have this background going into Calc 2 if you are taking that class. All right, what we have in number 4 here is just a constant, right? Summation of 3 as I goes from 1 to 30. Do you know what to do here without even having to list them out? If you said multiply the upper limit by 3, you are correct because you're adding 3 30 times basically. So 30 times 3 is 90. That is the answer to that question. All right, number 15 is going to give us a little bit more work. Summation of quantity 3k minus 1 squared summed over k equals 1 through 15. Now, yes, we could go to the calculator. Yes, we could do 1 by 1 and try to do it by hand. But let's try to use properties of sigma here, okay? So first thing I'm going to do is I'm going to distribute the 3k minus 1. I'm going to expand that out, basically FOIL it. 3k minus 1 times 3k minus 1, and you're going to get 9k squared minus 6k plus 1. And then distribute your sigma notation over each and every term here. And while I'll do that, I will also factor out the constant multiples. So I have 9 times summation of k squared minus 6 times summation of k plus summation of 1. In each case, k goes from 1 to 15, 1 to 15, and 1 to 15. And at this point, use the rules that we learned, like summation of k squared, k goes from 1 to 15. Remember, there the rule was n times n plus 1 times 2n plus 1, which would be 31 in our case, all over 6, minus 6 times summation of k. There the rule was n times n plus 1 over 2. Your n is 15, so it's going to be 15 times 16 over 2. And the last one is just a constant, so there, just multiply 15 times 1, it's just going to be 15. And you can do all kinds of simplifications or just directly enter these things into the calculator, but if you do that, you're going to get a final answer of 10,455. And so properties of sigma can be used effectively in simplifying expressions involving sigma notation and involving all kinds of polynomials like we've seen in this case. Okay, so we are one step closer to our goal of approximating area under a curve now that we're well equipped with all the different properties of sigma and have to simplify sums. So now we're going to tackle approximating area under a curve. So the typical question is going to be something like this. Find a shaded area, let's say over for under the curve f of x over the region from A to B, a finite region over the x-axis. And at the moment, we're only going to worry about positive curves, curves that are above the x-axis. And, you know, area has so many applications. It's not just geometrical meaning of it, but, you know, in physics, for example, area under the velocity function represents distance traveled, right? And in economics, area under a curve, for example, area under demand and above supply curves have certain meanings like consumer surplus or producer surplus. And you know, you can find the average value of a function, and there is a variety of applications you will see actually if you do happen to take calculus 2 as well. So it has many applications, so not just the geometrical meaning, okay? But how do we go about it? How do we find area when it's not a well-known geometrical figure? You know, a circle, a polygon, a triangle, there are formulas, right? But every time you write a function, an unknown function, you know, like it could be x squared, 5x cubed, whatever it may be, how do we find that area under the curve? Well, the idea there basically lies on doing what we know first. What we know is we know how to find area under we know area within a rectangle, right? So I'm going to try to go to this website right here. Okay, so let's say this is the curve. I'm trying to find the area under this curve from A to B. My A is 0, my B is 7. I'm going to try to fit rectangles that fit under this curve. Okay, right now there's just 4 rectangles that we are using here. And clearly 4 rectangles is not enough. There's a lot of overflows, underflows. We're not covering the total area under the curve very well here. So what I can do is I can increase the number of rectangles. Okay, so let n, the number of rectangles, instead of 4, say I have 7 rectangles now. I have 11, 12. Now I'm just going to go a whole bunch more. Take a look at what's happening. As the number of rectangles increase, we're getting better and better approximation under that curve, right? So the overflows and underflows are much, much smaller now. And we now have to find area of a rectangle, right? So if I could just add up the areas of all these rectangles, and don't worry, because we can do that using the summation notation. And we can, you know, instead of adding 1 by 1 by 1, we can just do it in mass using the properties of sigma. So if I could find areas of all those simple regions of rectangles, then I will end up with the area under the curve. And ideally, and this was a sticky point that, you know, mathematicians had to wait for centuries because Archimedes was able to do this up to n equals 96. He fit 96-sided polygon under a circle, but he stopped there. So it took mathematicians centuries, really even like almost 1,500, 1,600 years to come up with the exact answer because they had to understand how to deal with infinity. They had to have the tool known as the limit of a function as x goes to infinity. And because ideally what we're going to do is we're not going to stop at 96, but we're going to take a limit as the number of rectangles go to infinity. And in that case, we're going to have the perfect area, the exact area under the curve. So let's get started with baby steps, right? Let's just pick a very easy function, x squared, over the interval from 0 to 1, and try to find the area under this curve. And in the beginning, I'm just going to use 4 rectangles. But by the end of the segment, you're going to have the area using 4 rectangles under the curve, 10, 50, 100, and 500. And we're going to try to observe a pattern there, okay? And once you see a pattern, from there, we can try to make some generalizations. And this part can be a little bit challenging at first, but let me tell you that there are shortcut rules that are coming up, so do not be discouraged if in the beginning this seems a little bit confusing, because we're going to turn around, and when I introduce a shortcut rule, you're going to be able to do the same problem with this much easier technique known as the fundamental theorem of calculus. But to have appreciation for that, to understand where that's coming from, I'm also going to show you the step-by-step approach. And you may need to do that on the test just for one question, but for most of the problems, you're going to be able to use the shortcut rules, okay? So right now with 4 rectangles, so excuse me. So we're going to take the region from 0 to 1 and divide into 4 subregions. So I have a half and half of that on this side, half of this region on this side. So I have 4 regions of equal length. So 0, 1 over 4, 2 over 4, 3 over 4, and 4 over 4. So instead of 1, I'm writing 4 over 4. And in each case, I'm going to use the right endpoint to go to the function to get my height, and to obtain my rectangle, I go to the function at 2/4 also to get my height. So there's more than one way to do these. You can use right endpoints, left endpoints, midpoints. At the moment, I'm just using the right endpoints to get the height of the rectangle. And this is, again, the function y equals x squared function. So what is the sum of the areas of these 4 rectangles? So this is the first rectangle. This is the second rectangle, and so forth. Okay, notice that the base of each one is the same, right? The base of each one is 1/4. Going from 1/4 to 2/4, 2/4 to 3/4. Every one of them has a base of 1/4. So the base of the first rectangle is 1 over 4, and the height is, okay, you plugged it into the function to get the height, right? So that's 1 over 4 quantity square. And for the second rectangle, the base is 1 over 4. To get the height, we plugged in 2 over 4 into the function. So this is the squaring function. So that's how we get the height. Next one again, the base is 1 over 4. And the height, this time you're plugging 3 over 4 to go into the function to get the height. Again, it's the squaring function. So 3 over 4 square will give you the height there. And the last one, very similar. The base is 1 over 4. Height is 4 over 4 quantity square. Okay, now I could do this by hand. I could enter these on the calculator, but because we're trying to get towards n equals 10, 50, and so forth, it would be good to extract a pattern. So we can do this using sigma notation, possibly on the calculator even. So I'm going to write this as sigma notation. The 1 over 4 that comes up front does not change. So that 1 over 4, I'm just going to write it and take it outside of the sigma notation. Inside the sigma notation, I have 1 over 4 squared, 2 over 4 squared, 3 over 4 squared, and 4 over 4 squared. The numerator there is what's changing, right? So that's your variable. So x over 4 quantity square. But instead of x at the moment, let me just use I. So say I over 4 quantity square. And as I goes from where to where? From 1 to where? Since we have 4 terms, as I goes from 1 to 4, right? Okay. So technically, I can enter this into the calculator and I can get a result. Now for n equals 4, it may not be very important. You know, I could have easily entered these by hand, but remember, we're trying to get to n equals 500, so it's important to know how to do this with this method. And there are a couple ways you could do it. So you could go to the calculator and you could enter it in there. So I have the newer ones. I can do alpha y equals, and number 1 gives me a fraction. 1 over 4. If you don't have that, just enter 1 over 4 in parentheses on your calculator. Then I'm going to get summation notation under math, go all the way down or go up. So math, summation notation. And here I want to go, again, instead of I, I'm going to put an X equals 1 to 4. And the quantity I want to add is, I'm going to open another parenthesis here. I'm going to enter X over 4 quantity squared. And let's see what we're getting. So 0.4687, so roughly 0.469 is the sum of the 4 rectangles, 0.469. And that's a very crude estimate for the area under that curve, but it's a start. We're going to get better and better as we increase the number of rectangles to 10, 50, 100, and 500. So at this point, I would say please pause the video. Try to do the same thing now, this time area using 10 rectangles. So instead of 4, you're going to enter 10. So it'll be 1 over 10 times summation as I goes from 1 to 10 of I over 10 quantity squared. And then do this for 50, do it for 100 and 500. And fill out this table. And in a few moments, I'm going to reveal the answer. So please do that and come back to check your results. Something very interesting is happening, so I hope you'll take the time to do this. If you don't have your graphing calculator handy, you can also just go to Desmos graphing calculator, and right there, like you could enter, let's say 1, for division I'm just using the slash notation, 1 over 10. And then for sum, I'm just going to write the word sum in letters, and it turns it into a sigma. And n goes from 1 to 10. And if you open a parenthesis, we want to do, again, you could put I, X, whatever. I just put n, so I'm going to continue with that for the moment. So it was n over 10. It was quantity squared. So for power, I just shift caret symbol, and that's already showing me the answer right there, 0.385. So you can also do these things using Desmos calculator. So again, take a moment to finish the other two, please. So I do hope you took the time to do the other ones, and hope you were able to extract the pattern there. So I also did them, and I placed the numbers on the screen. As you can see, for n equals 10, we got 0.385. For 50, we got roughly 0.3434. For 100, 0.338. And for 500, 0.334. So do you see a pattern there? You know, as the number of rectangles increase, on the right hand side, the numbers got smaller, but they're not going towards 0, right? They're stabilizing around a unique value. Take a look, like from 10 to 500, we only went from like 0.38 to like 0.334. And from 100 to 500, it only went from like 0.34 roughly to 0.33 roughly, right? So it looks like they're stabilizing. So where do you think, if you had to take a guess, where do you think the limit is as n goes to infinity? So maybe you're guessing 0.30, you know, that would be a reasonable guess. Maybe you're guessing 0.33 or 1/3. Okay, so I'm going to hypothesize as 1/3. Okay, so the exact area is 1/3 as n goes to infinity. And I'm going to be able to prove that to you in a little bit. So we've used rectangles in the increasing number of rectangles to estimate the area under the curve. Now, I'm going to generalize this. So suppose we had n rectangles instead of just 10 or 50 or 100 or 500. So the base of each rectangle, instead of 10, it would be n, right? So it would be 1 over n. That would be the base. And the height of each rectangle would be, instead of like I over 1 or I over 20 or I over 50, but in the case of 50 rectangles, right now we're doing n rectangles, so it'll be I over n. And we're squaring because it's the squaring function, right? Remember, this is the base of each rectangle. Now this is the height of each rectangle. And we're going from 1 to n because right now we're doing the case with n rectangles. And how do we find the exact area again? We would have to take a limit as n goes to infinity. Okay, so we would simplify this and take a limit as n goes to infinity. Now, how do we simplify this? And sometimes I put r representing, we're using the right-hand side to get the heights. So to simplify this using everything we've learned so far in this lesson, So again, I have a bunch of rectangles here, basically n to be exact. And the base of each rectangle is 1 over n units. And the height comes by plugging in the function, that right endpoint, into the function. And if you compare this with the last page, when we had n equals 10, you're going to see we had 10 here, 10 here, 10 there. When we had 50, we had 50, 50, 50. So now we have n, so we wanted in general for n rectangles. So we got this pattern extracted. Now to simplify this, I'm going to first square this as I square over n square. And then I'm going to use properties of sigma to simplify. And at the end, we're going to take a limit as n goes to infinity to find the exact area. So if you simplify the inner portion of the sigma, it'll be I square over n square. And then 1 over n squared can be further taken outside because it doesn't depend on I. Here, I is the only variable. It's the lower index. We're using the letter I here. So now I have 1 over n cubed on the outside. And remember that summation I squared is one of our famous formulas. N times n plus 1 times 2n plus 1 all over 6. And then the question becomes, how do you take a limit of this quantity? Now, if you look on the top, n times 2n, if you multiply the highest degree terms, you're going to have 2n to the third, plus the lower degree terms. On the bottom, you have 6n to the third. If the degree of the top is equal to the degree of the bottom, do you remember how to take a limit as n goes to infinity? How do you take a limit of this as n goes to infinity? If the degrees are equal, you take a ratio of the leading coefficients, right? And what does that leave you with? 2 over 6, which is the same as 1/3. So that was the answer we got with the numerical approach. And with the analytical approach, we are able to confirm that. So if you're guessing, maybe it's 0.3, not 0.33. Well, this ought to convince you that it is indeed 1/3, the exact area under the curve. All right, so in the next segment, I'm going to go over with you the shortcut rules, known as the fundamental theorem of calculus, and you're going to be amazed how we can arrive to the same answer in a matter of seconds. So hope to see you in the next segment.